Welcome to this presentation. In this video, I am going to share with you the concepts of design of power amplifiers. Power amplifiers are used in the final stages of radar and radio transmitters to increase the radiated power level. So typical output powers may be of the order of 100 to 500 milliwatts for mobile voice or data communication system, or in the range of 1 to 100 watts for radar and fixed point radio systems. So important consideration for RF and microwave power amplification are efficiency, gain, intermodulation, distortion and thermal effects. So single transistors can provide output powers of 10 to 100 watts at UHF frequencies, while devices at higher frequencies are generally limited to output powers less than 10 watts. So the various power combining techniques can be used in conjunction with the multiple transistors if higher output powers are required. So far we have considered only small signal amplifiers where the input signal power is low and that the transistor can be assumed to operate as a linear device. So the scattering parameters of a linear devices are well defined and they do not depend on the input power level or output load impedance. A fact that greatly simplifies the design of fixed gain and low noise amplifier is this. Okay. So for high input powers, for example in the range of 1 dB compression point or third order intercept point, transistor do not behave linearly. So in this case, the impedances seen at the input and output of the transistor will depend upon the input power level, and this will generally complicates the design of power amplifiers. And now let us see the characteristics of power amplifiers. And the power amplifier is usually the primary consumer of DC power in most handheld wireless devices. So amplifier efficiency is an important consideration. So one measure of amplifier efficiency is the ratio of RF output power to DC input power. That is, eta is given by P out divided by P DC. This quantity is sometimes referred to as the drain efficiency. And one drawback of this definition is that it doesn't account for the RF power delivered at the input of the amplifier. Since most power amplifiers have relatively low gains, the efficiency tends to overrate the actual efficiency. A better measure that includes the effect of input power is the power added efficiency, and it is defined by eta PAE, that is power added efficiency, is equal to P out minus P in divided by P DC. That is equal to 1 minus 1 by G into P out by P DC. That is equal to 1 minus 1 by G into eta, where G is the power gain of the amplifier. Silicon power bipolar transistor amplifiers in the cellular telephone band of 800 to 900 megahertz band have power added efficiency on the order of 80%, but efficiency drops quickly with increasing frequency. So power amplifiers are often designed to provide the best efficiency, even if this means that the resulting gain is less than the maximum possible. And another useful parameter for power amplifiers is the compressed gain. And the compressed gain is defined as the gain of the amplifier at the 1 dB compression point. Thus, if G0 is the small signal linear power gain, we have compressed gain as G1 of dB is equal to G0 of dB minus 1. So non-linearities can lead to the generation of spurious frequencies and intermodulation distortion, and this can be a serious issue in wireless transmitters, especially in multi-carrier systems where spurious signals may appear in adjacent channels. So linearity is also critical for non-constant envelope modulation such as amplitude shift keying and higher order quadrature amplitude modulation methods. Class A amplifiers are inherently linear circuits where the transistors is biased to conduct over the entire range of the input signal cycle. Because of this, Class A amplifiers have a theoretical maximum efficiency of 50%, and most small signal and low noise amplifiers operate as Class A circuits. So in contrast, the transistor in a Class B amplifier is biased to conduct only during one half of the input signal cycle. Usually two complementary transistors are operated in a Class B push-pull amplifier to provide amplification over the entire cycle. And the theoretical efficiency of a Class B amplifier is 78%. And class C amplifiers are operated with the transistor near cutoff for more than half of the input signal cycle and generally use a resonance circuit in the output stage to recover the fundamental. And class C amplifiers can achieve efficiencies near 100% but can only be used with constant envelope modulations. So higher classes such as class D, E and F and yes, they use the transistor as a switch to pump highly resonant tank circuit and may achieve high efficiencies. The majority of communication transistors operating at UHF frequencies or above rely on class A, AB or B power amplifiers because of the need of low distortion products. Now let us discuss about some large signal characteristics of the transistors. A transistor behaves linearly for signal pass well below 1 dB compression point, and so the small signal scattering parameter should not depend on either the input power level or the output termination impedance. However, for power levels comparable to or greater than IP1 dB, where the nonlinearity of the transistor becomes apparent and the measured scatter parameters will depend on the input power level and the output termination impedance. Thus, large signal scattering parameters are not uniquely used in place of small signal parameters. For device stability calculations, small signal scattering parameters can generally be used with good results. Okay, and a more useful way to characteristics the transistors under large signal operating conditions is to measure the gain and output power as a function of source and load impedance. One way of doing this is to determine the large signal source and load reflection coefficient, that is tau SP and tau LP, and that maximize the power gain for a particular output power. And another way of characterizing the large signal behavior of a transistor is to plot the contours of constant power output on a Smith chart as a function of the load reflection coefficient, that is TLP, tau LP, with the transistor conjugately matched at its input. And these are called load pull contours, and they are obtained using an automated measurement setup with computer controlled electromechanical step tuners. And load pull contours are similar in function to the constant gain contours, but they are not perfect circles due to the nonlinearities of the device. Nonlinear equivalent circuit models can also be developed and used to predict the large signal performance of FET and BJTs. The dominant nonlinear parameters for a microwave FET are CGS, GM, CGD and RDS. We know these parameters very well. CGS means gate to source capacitance, transconductance, and gate to drain capacitance and drain to source resistance. So an important consideration in modeling large signal transistor is the fact that most parameters are dependent on temperature, which of course increase the output power. Equivalent circuit models can be very useful when combined with the computer aided design software. Right. And now let us see the design of a class A power amplifier. Since class A amplifiers are ideally linear, it is sometimes possible to use a small signal scattering parameters for design, but better results are usually obtained if large signal parameters are available. As with small signal amplifier design, the first step is to check the stability of the device. Since instabilities begin at low signal levels, small signal scattering parameters can be used for this purpose. Stability is especially important for power amplifiers, and as high power oscillations can easily damage active devices and relative circuitry. The transistor should be chosen on the basis of the frequency range of and power output. Ideally about 20% more power capacity than is required by the design. Okay, and silicon bipolar transistors have higher power outputs than gallium arsenide FETs at frequencies up to a few gigahertz and are generally cheaper. GaN HBTs are becoming very popular for high power applications and at RF and low microwave frequencies. And the transistor should be chosen on the basis of frequency range and power output, ideally with about 20% more power capacity. Okay, and this could be compared with the design of class B power amplifier. where in this class A amplifier, we can note that the values are approximately equal to the large signal values, that is tau SP and tau LP, but not exactly due to the fact that the scattering parameters used to calculate tau S and tau L do not apply for large parallels. So we should use the large signal reflection coefficients to design the input and output matching networks. And for an output, for example, for an output power of 10 watts, we require input drive power is nearly about 220 milliwatts. So the DC input power can be found from the drain efficiency by the formula P DC is equal to P out divided by 8, right? So the class A amplifiers are ideally linear, and it is sometimes possible to use the small signal parameters, scattering parameters here for design, but better results are usually obtained if large signal parameters is available, right? And nonlinear equivalent circuit models can also be developed used to predict the large signal performance of FET and BJT. The dominant nonlinear parameters for a microwave FET are, as I said earlier, they are the CGS and DGS. So which of course increases the output power. Equivalent circuit models can be very useful when combined with computer aided design software. Thank you.